So in this episode, we will talk about liveness. So safety properties are cool. They ensure that the invariants are upheld in every single state. But there are certain properties we want to verify that spans across many states, right? And then so this is where we want to use liveness, define liveness properties that we can verify. So for example, in a gossip protocol, we want to make sure that eventually all the nodes in the cluster they are moving forward, right? Or going back to the elevator example we talked in earlier episodes, we want to make sure that it always goes to the higher floor, right? And then so these are properties that you cannot verify by looking at any given state, right? You have to look at a series of states to conclude whether these properties are upheld, right? So in my opinion, this is actually it's a superpower, right? It's a TLA plus a superpower, right? You could verify very cool things with it. The downside is, at least at the time of this episode being recorded, liveness property, like it's implemented using a strongly connected component algorithm, and then the way it's implemented right now, it's sequential, right? So verifying liveness property with the model checker as of right now takes a very long time, simply because it's bound by a single threaded execution, right? But nonetheless, so we'll briefly talk about some temporal formulas that you could use to describe liveness in your system. So we'll start with this example, right? So hopefully fairly trivial. We have a state machine. So we go, state from 1 can go to 2, 2 then go to 3, and 3 can go back to 2, right? And then that's described using the spec that's illustrated here. So as usual, as we talked about in the previous episode, you have to have a fairness description to sort of drive the state machine forward. In the absence of it, it's possible for the spec then permits inaction, right? You can simply stutter and don't do anything. So at least for example, we're providing a minimal fairness description just so we could drive the state machine forward. Okay, so now what do we want to verify, right? And then so looking at this state machine, so let's just say that we want to make sure the state machine always eventually go to state 3, right? And then hopefully looking at this diagram, it should be fairly self-explanatory, right? So we go from 1 to 2, 2 to 3, 3 may go back to 2, but we always eventually hit 3, right? And then so that is described using this semantic, right? So the square is, the box operator is always, right? And then the diamond operator is eventually, right? So the state machine always eventually settled to counter equal to 3, right? Or I guess state equal to 3 in this case. But again, note that, it's not actually, it doesn't remain in state 3, but that's okay, right? Because our property requirement here is always eventually. We've hit it once, right? And then so we already satisfied, the property requirement. But what if we switched operators around, right? So what if we, switch these two around, right? So what if it becomes eventually always? So now it's a little bit different, right? So eventually always then implies that it has to stay in the third state, right? So if we enable eventually always counter equal to 3 or state equals to 3, per this diagram state definition, it will actually fail, right? Because it does not remain state 3, because it's remain in a loop of 2 and 3. So to satisfy eventually always, we actually need to update, for this example, update the state definition. So we remove the loop going back from 3 back to 2, right? So if we update the diagram to look like this, 1, 2, 2, 3, then the eventually always would be satisfied. So hopefully that makes sense so far. For this particular example though, right? So looking at this diagram right here now, so 1, 2, 2, 2, 2, 3. This diagram now satisfies eventually always, but it also satisfies always eventually, right? So in this particular case, one is a subset of another, right? That's not to say this is always true, right? Like there may be For example, in I think in what is in gossip protocol here, right? Like there are examples where the state may not settle onto a certain fixed state, right? Like I think in the gossip protocol example, the individual nodes, even once they've hit the highest state, the node may restart, right? Like it may not persist, like the system may not persist, even once it hit that eventuality requirement, right? And then so when you construct your property, you got to be a little more careful on what you're actually trying to verify. So the last operator I want to quickly temporal phone I want to quickly talk about is the leads to, right? So the leads to operator, which is the squiggly tilde arrow, I guess, it's a cause and effect description, right? And then so you describe it like this, right? So if we ever were in state 0, it will eventually lead to state 3, right? So hopefully that's obvious, right? Going back to this, right? But if we say that if we start from 0, we can only go to 4, this is clearly false, right? Because we will never make it to state 4, right? The other thing to note here is the evaluation only takes if the left side of it, right, is if the counter equal to 0 is true, right? If counter is not like if the left side of it is never true, then this whole thing is moot, right? So if the left side is false, this whole thing is always true, if that makes sense, right? So in this case, if the model checker, if we declare that counter equals to 4 or state equals to 4 always leads to 3, this is actually always true, right? Because we're never in a state where state equals to 4. So that's it for this episode. Again, thank you for watching. Bye.